Good morning to all. On behalf of PG and Research Department of Mathematics, DJ VAISHNAV College, I welcome everyone to the 11th session of C4 Chase, Crack, Conquer, CSIR Net. Prayer is an opportunity to spend time with God. We will start our session with Tamil Thai Vaathu, followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழே எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் திகழ்ந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं धृतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिस्ततां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनाम विभेदेन जगत्क्रीडति यो यतः ओम शांति शांति शांति.
Once again, I welcome to all our 11th C4 session. Today, our resource person, Dr. N. Sridharan, retired professor and head, Department of Mathematics, Azhagappa University, Karaikudi. I welcome you, sir. Now, I hand over the session to our resource person.
Thank you, Professor. Thank you, Professor. Good morning to all. Today we are having to go to the third lecture on complex analysis. This is a continuation of the previous one. It is also about analytic functions. Last one we stopped with the Leibniz theorem and maximum modulus theorem. Now we will start with the Sparks lemma and other things, application over these things. So now I will go to Dana. என்ன பண்ணும் PowerPoint
போயிட்டு நீங்க இல்ல சார் PowerPoint
என்ன பண்றது?
No.
அதுதான்
Yes, sir. They close my eyes.
ரிக்வஸ்ட் பண்றேன்.
Close my eyes.
அதான் ஒண்ணு எனக்கு
Yes, sir. Or just close my eyes. திருப்பியும் போடலாம் சார்.
ஏன் ரிக்வஸ்ட் பண்ணுமா?
Slide show.
Okay.
Okay.
Thank you. Are you able to
Yes, sir. Audible, sir. Yes, sir.
see that
Yes, sir.
board?
Yes, sir. Visible,
Oh, sir?
sir. Yes, sir.
Are you
Voice
able to
also-
see the board?
Slide also
Okay,
okay,
okay.
sir. Okay, sir. Thank you. sir.
Okay. Okay, very good. Thank you, thank you, thank you. This is a continuation of the previous lecture. This is a third lecture. Let us recall what are the theorems we have done in the previous one. Most important theorem is Liouville's theorem. If f is a bounded entire function, then it must be a constant function. We have seen this, and we have used this to do many problems of the net thread examination problems using this. But Liouville's theorem says that if the entire function, it must be a constant function. Bounded entire function is a constant function. That means non-constant entire function is unbounded, that's all. But Little Picard's theorem says something more than this. The image of a non-constant entire function is the entire whole complex plane or entire complex plane minus a single point. The image can omit at most only one point from the complex plane. If it omits two distinct complex numbers alpha and beta, then the function should be a constant function. This is called Little Picard's theorem. If f is an entire function, and if there are two distinct complex numbers alpha and beta, which are not in the range of f, then f is a constant function. Using this, we can do a lot of problems. You need not bother about the proof of this theorem. Just assume this theorem. We can do a lot of things. Say, for example, if it's an entire function f is given, and it is not taking any real value, that is f of z is not real for any z, then the image omits the real axis. It contains other things. Since the real axis contains more than two complex numbers, the function reduces to a constant function. We have seen these things last one. And another important theorem is maximum modulus theorem. If f is a non-constant analytic function in region, what is region? Region is a connected open set. If it is a non-constant analytic function, then what about the modulus of f of z? Mod f of z attains no maximum in omega. That means, given any point z0 in the region, I can find mod f of z0. There is some other point z1 in the region whose modulus value, mod f of z1, is strictly greater than mod f of z. So, there is no maximum on this. This is over the region omega. If the region is bounded region, then I can find the boundary of that. The function attains a maximum on the, because if it is a bounded function region, its closure is a compact set. The continuous function is bounded on the compact set. So it attains the maximum value. It attains the maximum value only on the boundary. If the function is not constant analytic function defined on a bounded region, then the maximum is attained only on the boundary of the function k. So, okay, using this also we have done many things. Now we'll come to this one, Scott's lemma. Using the maximum value theorem, we can find a new theorem, the Scott's lemma, which is the most important theorem in the complex analysis. The entire theory of force depends on this. If f of z is function defined in the unit disk, mod z less than 1, and satisfy the condition f of 0 is 0, and mod f of z1 is less than or equal to 1, that means the image of the unit disk is within the unit disk, then mod f of z, what is given there, mod f of z less than or equal to 1. But he concludes that mod f of z less than or equal to mod z for all z. And also mod f dash of 0 less than or equal to 1. This is the conclusion of the theorem. If f of 0 is 0 and mod f of z is less than or equal to 1, then mod f of z less than or equal to mod z, and also this. Suppose it is equal to, this inequality is equal at some place, and also or this is equal, then what will happen? It should be a constant function. Okay. either f of z naught equal to mod z naught, that is equation, but at some point z naught is not 0, because at 0 it is given already there. F of 0 is 0 already there. Therefore at 0, okay. Other than that point, if there is a z naught like this, or this is equal to 1, then the function is a constant function. Okay, not constant function. The function is f of z is lambda z for all z, where lambda is a fixed complex number with mod 1. Actually, we are in the proof, we are going to prove that lambda equal to this f dash of 0. F dash of 0 is already given, that lambda equal to f dash of 0. We are going to prove that condition. Okay. Now, f of z be analytic in mod is less than 1. This is the statement. Once again, what is the meaning of the statement? The statement is f is defined in this disk. Now consider a smaller circular disk here with radius r is less than 1. Then image of this disk lies within that. What is the previous one? Image of the unit disk is within unit disk. But it says that further, for every smaller disk with a radius less than 1, the image of the disk is also within that small disk. That the image contains within this. That image contains within this. It goes like that. This is the interpretation of this. There is the Scott's lemma. But the proof of this theorem is important because they are asking many questions in net examination using the technique of this proof. We are not going to see the proof of many other theorems, but this proof of the theorem is more important because there are a lot of net questions asking about the using this proof. What is the proof given? F of z is analytic. Therefore, I can find a Taylor's expansion for f of z in mod z less than 1. But f of 0 is 0 is given. Therefore, f of 0 is 0 here. So f of z equal to f dash of z naught by factorial 1 inside from f double dash of factorial 2 z square, etc. So first term is 0. Therefore, I can take z outside. So I take z outside, I get the remaining. The remaining is also analytic function. So I write f of z equal to z into g of z in z. This g of z is analytic. What is g of 0? What is g of 0? G is this function. G of 0 is f dash of z is 0, therefore f dash of 0 here. So the g of z satisfies the condition f of z, g of z equal to f of z by z, provided z not equal to 0, and if z equal to 0, f dash of 0. It is an analytic function given. Therefore, we need not check with the other thing because it is written like this. It is an expansion of Taylor's expansion of g here. Therefore, it is an analytic function. So now I consider a small circle here with the radius r. I fix z. I fix z, take some radius r bigger than that, but less than 1. Z lies in a smaller circular disk. So what is g of psi on the boundary? G of psi is less than equal to, what is g of psi on the boundary, on the smaller circle here? G of psi is equal to f of psi by psi. But f of psi is less than equal to 1. That is a given condition there. Therefore, it is 1 by psi. But psi is a point on this. Mod psi is the radius of the smallest circle, therefore it is r. So g of psi is mod g of psi less than 1 by r. So on the boundary, the value of mod g of psi is less than 1 by r. Since we know the bounded region, maximum is attained only the boundary. So inside it is less than equal. So the maximum value is also less than equal to 1 by r. Maximum value is also less than equal to 1 by r. Therefore, for interior points also, the value is less than equal to the maximum value, which is less than equal to 1 by r. Okay. So what will happen? G of z for all these points, z is 1. So mod psi is 1. So maximum value is 1 by r. So the maximum modulus theorem mod g of z is inside this. The maximum is only attained on the boundary. So this is less than equal to the maximum value is 1 by r. So this is given here. Therefore, what is g of z? G of z, what is given there? It is true for all z. Therefore, g of this is 1 by r. As r tends to 1, as r increases, r is half, r increases to 1. This right hand side tends to 1. Therefore, g of z less than equal to 1. Okay, right? G of z, okay, g of z less than equal to 1. Therefore, what will happen? G of z mod g of z less than equal to 1. Mod g of z is nothing but f of z by z. Therefore, mod f of z less than equal to mod z. That is true for even for z equal to 0. I get that I have omitted mod z here. So mod f of z less than equal to mod z. Okay, and this is true for f of 0 is 0 here, therefore that is true for that also. So f dash of z equal to g of z is less than equal to 1. So I get the first result of that. Now if further, suppose this is equal to f of z mod f of z naught equal to mod z naught for some z naught, then the function is a constant function. Which function? G is a constant function. G of that means it attains a maximum interior. The maximum interior function should be constant. Non-constant function should not attain the maximum in the interior. Since G attains the interior maximum at the interior point, G of is a constant function, G of is equal to lambda, where mod lambda equal to 1 because the value is 1 here. So mod lambda equal to 1 here. So G of z equal to lambda. So f of z equal to lambda z for 0 less than equal to 1. This is true for z equal to also, and f dash of z equal to lambda. Okay. In this case, when it is attains a maximum, the lambda is not different. Lambda is f dash of 0. The function is unique. This is a proof of the Schwarz lemma. Okay. Okay. Now let us make what is the Schwarz lemma says. Schwarz lemma says that f of 0 is 0. That's all. 0 is a point function for 0 is a 0 for the function f at 1, but the order is not given. F dash of 0 may be 0. F double dash of 0 may be 0. For example, here we have assumed that f of 0 is 0. Suppose f dash of also 0, f double dash is also 0. What will happen? So, but f is a non-constant function. Therefore, there is at least one fm of 0 not equal to 0. That m is the order of that. If we know the order, we can see something more. Okay, here f of z 1, f of z has a 0 of order m at 0. It gives that f of 0, okay, f of 0 is 0, f dash of 0 0, f n minus 1 is also 0, fm of 0 is the first derivative which does not vanish at 0. Okay, and the conclusion of this theorem is mod f of z less than equal to mod z. What is the previous theorem? Schwarz lemma. Mod f of z less than equal to mod z. There we assume that f of 0 is 0. That's all. But here it is an order m. Therefore, mod z power m. Note that mod z is less than 1. Therefore, mod z power n is less than, strictly less than mod z. Okay. Therefore, this is conclusion is f of z less than equal to 1, and this is f dash of 0 is less than equal to m factorial. If m is 1, it is 1. Okay. So it is an expansion, generalization of the Schwarz lemma. Further, if they are equal, then the g should be constant function. Say f of z equal to lambda z power m. Schwarz lemma says that f of z lambda z. But if the order of z equal to 0 is m, then z power m is here. So this is the just a straightforward expansion of the theorem. Okay. Okay. The proof is same thing, because we start f of z start with first few terms 0, start with fm of 0. So I can take z power m come outside. That lemma we have taken z only, but here z power m is common to all. Therefore, z power n into g of z I can take it. G of z the remaining. The proof runs similar way. Only thing is z power n into g of z, that is z into g of z. Therefore, f of g of z is going to be constant. Therefore, f of z equal to lambda times z power n, but mod lambda equal to something else. Okay. So we are going to, this is just extension of that. The another extension is, previously that is defined only on the unit disk. Now f of z is defined on the disk with a radius r with a center 0, and f of 0 is 0. So instead of 1, I have taken r. And what is given there in the one mod f of z less than 1 there. But instead of that, f of z less than m. So image of some circle goes to the image of another circle within the another circle with f of 0. 0 goes to 0. Center is not changed. F of image of 0 is 0. Then what will happen? Then this is m by r. A mod f of z is equal to m by r into mod z. There r is also 1, m is also 1 in the original lemma. Therefore, we get this. So instead of this, I get m. That m is the radius of the image circle. This r is the radius of the original domain. So mod f dash of is m by n. Okay. The proof, the same thing. The conclusion of this is this. Conclusion is this. For that, what we are doing it, I want to use this Schwarz lemma. Schwarz lemma defines a function from a unit circle to unit circle, but we have given a function in the bigger circle, and image is also another bigger circle. I want to convert this f from unit circle to unit circle. So from unit circle to big circle, I get a map. What is r is it? Just expand. Half goes to r is r of like that. Just expand for this, for this. This instead of 1, I have to increase the distance by r. So by this expansion map, so this disk is unit disk is mapped onto the entire disk of radius r. Then use f. But this radius is m. So reduce the radius. So z by m. So by multiplying by the radius, using f and reducing the radius, I get a map from to this. That is a G. What is a map G? G is a composition map. First z, r z, f of r z, and by m. The map is this. The map is given by this. Okay. Now G is a map from circle to circle. G of 0. 0 goes to 0 because z is 0. 0 goes to 0. There also given f of 0 is 0. 0 goes to 0. So the condition is satisfied. Therefore, mod g of z less than equal to mod z. Here, I get the map psi. Mod g of psi less than equal to, I get mod g of psi less than equal to psi. Psi is a point here. But given psi, I get r psi. I get the image f of r psi. I get here f of r psi by capital M. F of r psi by capital M. So mod is equal to f of capital M. That condition is this. So this is just an extension of that. Okay. Now, we want to work on many problems given under this lemma. For that, we need something more. Now, consider the unit circle. Alpha is a point in the unit circle. I consider the map, bilinear map. Phi alpha z equal to z minus alpha by 1 minus alpha z. When is z equal to alpha, this is equal to 0. Therefore, phi alpha equal to 0. When z equal to, when this is equal to 0 only when z equal to 1 by alpha bar, it is outside the unit circle. Therefore, this function is analytic in the unit circle. So this map carries the unit circle into unit circle. What about the modulus of this? Modulus of this is 1 when mod z equal to 1. Therefore, this maps a unit circle into unit circle. Interior of the circle to interior circle. Outside the circle to outside circle. So this map is 1 to 1 onto map from U to U. But Schwarz lemma says that f of 0. But here what is given? Phi alpha is 0. Okay. And the inverse map of alpha is just replace alpha by plus this. I think the inverse of phi alpha is this. Then because this is an analytic function, I can find the differentiation by u by b method. V square u dv minus v du formula. Substitute, this is the one. If I substitute here z equal to 0, I get the value z equal to 0. I get the value 1 minus alpha. This is 0, 1 minus alpha square mod alpha. Alpha bar is alpha mod alpha square. Okay, this is equal to 1. If we put alpha here, this is equal to 0 here. Okay, alpha bar is 1 minus alpha square. This is alpha, this square is there, that is cancelled. I get this 1 minus mod alpha square. So this result is a known result in binary transformation. Consider this binary transformation where alpha is a given point in the unit circle. Then this map maps phi alpha into unit circle, inside into inside. It is a 1-to-1 onto map, and the phi alpha is 0. Inverse is this thing. The last one I'm going to use in the problems. Okay. Now U is a unit open disk with a model less than 1. It's a unit disk, and F is analytic function. Okay, the theorem lemma says that f of 0 is 0. F of 0 is 0 means then we have concluded mod f dash of 0 less than 1, less than or equal to 1. But here, if the value of f alpha is known, how to find the maximum value for that? They are given that f of 0 is 0. Then I know mod f dash of 0 is less than or equal to 1. So if we know f of 0, I know the maximum value for f dash of 0. Here the same thing. Question is, for any given alpha, if I know f of alpha, what is the maximum value for the modulus of the derivative f dash of alpha? The answer is this. This answer, please, students, please note this answer. For the most of the problems, we are going to use this formula. The maximum value for f dash of z mod f dash of alpha less than or equal to 1 minus mod alpha square by 1 minus alpha square. What is given? Alpha is known, f alpha is known. Therefore, I can find the right hand side. The f dash of alpha less than or equal to that value. If they will ask like this, is there any function f dash of alpha greater than this value? No. Okay. For this inequality is more important. The students who are aspiring to appear for the net examination, please note this. Okay, record this. I'll give the proof for this, but don't bother about the proof. But this formal inequality is more important to tackle questions regarding Squar's lemma. Okay. How we are going to this? I'll give the sketch the proof for this. Okay. Now, G is given here, F is given here, alpha is a map, F of alpha is something, it is given. F is a map from unit circle to unit circle. I know F alpha is given, I know its value. It is not 0, it is something. But I want to use Squar's lemma, so I want to make alpha 0 and make this 0. Therefore, I consider once again unit circle. I consider a map which takes 0 to alpha. Here, that map I already have noted that phi of minus alpha. There are plenty of maps, but I use this map because I know this binary transformation which takes the origin to alpha. Therefore, I consider this. Okay, and map this. This beta, I want a map from here to here such that beta goes to 0. This side map is a phi of minus beta. The opposite inverse map is phi of beta. So phi of minus alpha takes a 0 to alpha here. F takes alpha to some value, given value. I call that as a beta. That beta has been taken to 0. Therefore, the composition map takes 0 to 0. So I get a map G, which is analytic from the unit disk to unit circle, and G of Z equal to 0. Therefore, I can use the Squar's lemma. So I apply the Squar's lemma, I get a G of 0 is 0 here by composition. By Squar's lemma, mod G of Z less than equal to Z and mod G of 0 less than equal to 1. So this formula I want to use. What is G dash of 0? What is G is just composition. So G of 0, G dash equal to this dash at f of 0 and dash at 0 like that. So this is given by the G dash of 0, but this is a composition map. So derivative is given as a chain rule. F dash of beta into beta, f dash of alpha into f dash of this. I know the value. The value is 1 minus beta square. Previously I have noted that. This is phi dash of alpha is 1 by this. Phi dash of 0 is this. I used that formula here. Okay. Sorry. that formula here. So b dash of beta is 1 by beta square. F dash alpha beta, I don't know, that is given here. This is equal to. Therefore, what is the value of this? This value less than equal to 1 is given. Therefore, this modulus is less than equal to 1. So modulus of 1 minus beta square already a positive number. Because beta is a number in the unit disk. Therefore, 1 minus beta square is positive. Okay, mod f dash of alpha into this is less than equal to 1. So mod f dash of alpha less than equal to this. So this is the value here. That is given that this is mod f dash of alpha less than equal to 1 minus f mod f dash. This is the question. Okay. Okay. Now we are summarizing this also. U is a open disk and alpha is a point. Question is, does there exist an analytic function from here where f of alpha is beta, f dash of alpha is also given. So f the alpha is given point. Its image, I know the derivative f dash of alpha u. Okay, does that exist? Just I want to compare inequality. That's I'll put in the value in the inequality. What is here? F dash alpha is mu here, and 1 minus beta square here. Their inequality is less than equal to. If this is greater than equal to, that means this does not satisfy inequality. Therefore, conclusion is there is no such analytic function. If mod mu is greater than equal to the inequality, then there is no such function. If it is equal, then there is a function. That function is unique. You can conclude that. If it is less than or equal to, there is a function. If it is equal to this, left hand side equal to right hand side in the inequality, if inequality becomes an equation, then there is a unique analytic function satisfy this property with what? F of alpha is beta, f dash of this. With the given data, if these conditions are satisfied, then the function exists and it is unique. And that is the unique function is given by this formula, because already I have noted that previously. Okay, I have noted that. What is that? This is this is given here. Therefore, I want to find f. So I take phi alpha inverse and that side. Therefore, I get this. Okay. Okay. If so, this is a formula. So lambda is less than equal to this. That is f of z is given by this. I know alpha, I know beta, therefore I know all these things. What I don't know lambda. Lambda I take this. What is that? 1 minus alpha square. This is I want to invert this, because 1 minus alpha square by 1 minus beta square into given value mu. This modulus is 1. This is mu. Okay. So if this is less than equal to, what will happen? If this is strictly less than, then also the function exists. Function does not exist only when this inequality is satisfied. If this is less than equal to 0, less than equal to right hand side, always exists. If it is equal, it is unique. If it is strictly less than, then function exists. There are infinitely many functions satisfying this condition. Okay. Okay. Such a function also given by this same formula. One such function can be given, but there are other lot of functions are also there. Okay. Okay. One minute. The question is this: does there exist an analytic function? This is a net question. Does there exist an analytic function f d to d such that f of half equal to 3 by 4 and f dash of half equal to half? Just I want to, I know alpha, f alpha, I know the value beta, I know the value f dash also. So I want to substitute in the inequality. Here alpha is half, beta is f of alpha is 3 by 4 given, mu equal to this. The inequality is this is the inequality. Bound for that is 1 minus beta square by this. Substitute 1 minus 9 by 16. Beta is 3 by 4, therefore 9 by 16. Alpha is half, therefore 1 by 4 equal to 7 by 12. But what is given here? 1 by 2. This is 7 by 2, 1 by 2, which is smaller. 1 by 2 is 1 by 6 by 12. 6 by 12 is less than 7 by 12. Therefore, the given value is less than this. Therefore, there are many functions. The inequality is strictly less than. This value is less than this bound. Therefore, function exists. There are infinitely many functions. Okay. There are many such functions satisfying this property. Okay. One such function is this. I have given the formula. That formula, substitute the formula. Phi of 3 by 4, lambda 3 by 4, where lambda is this is the value. 3, okay, minus 3 by 4. There the lambda value I have calculated. Because alpha known, beta known, mu known. Therefore, the value equal to 6 by 7. Therefore, the lambda is 6 by 7. Substitute this. I know the value for this function. I know the function here. This is one such function. There are many other things also for these things. Okay. Okay. There is one question. D be the unit disk with mod is less than 1. Does there exist only function f d to d such that this is the condition? This is a third question. D is a disk, unit disk. F d to d such that f of half equal to 3 by 4, f dash of half equal to 2 by 3. This is one question. Can we find f satisfying this property? Second question, 3 by 4, f of half is 3 by 4, f dash of half is 5 by 12. Can we find f? Third question, 3 by 4 image equal to minus 3 by 4, derivative is minus 3 by 4, f of 0 is half and f dash of 0 is 3 by 4, f of 0 is 0, f dash of 0 is 2. Okay. So we want to find out the answer for each. Does there exist f satisfying this property or this or this? Only thing is I know alpha. What is alpha? Alpha is half. I know beta. Okay. I know mu. Mu is 2 by 3. Alpha known, beta known, mu known. Satisfied, substitute in the derivative, substitute in the inequality. If the inequality is satisfied, yes. Inequality is not satisfied, no. For all these 5 problems like that, I have tabulated the answer here. For the first problem, alpha is half, beta is 3 by 4, mu is 2 by 3, it is given data. I have substituted this 7 by 12, okay. The value 2 by 3, this is 7 by 12. 2 by 3 is 8 by 12, is strictly greater than 7 by 12. Okay, strictly greater than, therefore, the inequality is not satisfied, the answer is no. Second problem, alpha is half, the value beta is 3 by 4, mu equal to 5 by 12. Find out the right hand side of the inequality, 1 minus beta mod beta square by 1 minus mod alpha square. That is 7 by 12. Compare with this. This is 5 by 12. This is 7 by 12. Therefore, this is smaller than this. Therefore, inequality is satisfied. Therefore, yes, that you are not asking to find the function. Your answer is yes or no. Since this is smaller than this, there are a lot of functions. Answer is yes. The second one, third one, alpha is 3 by 4. For example, the third one, alpha is 3 by 4, beta is minus 3 by 4, mu equal to minus 3 by 4. Okay. Third one, 3 by 4, minus 3 by 4, minus 3 by 4. The inequality is 1. Modulus, minus 3, don't compare minus 3 by 4. Modulus of this, mod mu, is 3 by 4 less than 1. Is answer is yes. Because this is smaller, modulus value is smaller. The fourth question, 0, half, 3 by 4. The answer is 3 by 4. They are equal. Then also answer is yes. But in this case, there's a unique function. Whereas this case, the previous case, the functions are not unique. Because this is strictly less than, this is strictly less than, therefore. The second case, 0, 0, 2. This is 1 minus 0 by 1. 2 is greater than 1. Therefore, inequality is not satisfied. Therefore, answer is no. Okay? This is already seen. Okay. Now, let f be a harmonic function from unit disk to unit disk. What is given there? F of 0 is 0. Therefore, I can use the Scott's lemma, where D is open disk. Okay. Which of the following is correct or wrong? Mod f dash of 0 is equal to 1. Mod f of half is less than equal to half. Mod f of half is less than equal to by 4. Mod f dash of 0 less than equal to half. This is f of 0 is 0 and function is analytic from unit disk to unit disk. Therefore, Scott's lemma hypothesis is valid. By Scott's lemma, what will happen? Mod f of z less than equal to mod z. And mod f dash of 0 less than equal to 1. Okay. Mod f dash of 0 less than equal to 1. It need not be equal to 1. It may be half. Therefore, mod f dash of 0 equal to 1 is not always true. Because it is true for all such functions. Any function satisfying this is true. This is true only for few functions, for not other functions. So that theorem says that mod f dash of 0 less than equal to 1 only. It is equal to 1 is wrong. Second one, mod f of half less than equal to half. If you said mod f of z less than equal to mod z, it is given there. Mod half is half. Therefore, this condition is satisfied. This is by Scott's lemma, mod f of z less than equal to mod z. Therefore, true. Mod f of z less than equal to 1 by 4. No. It is less than equal to 1 by half. That is all given. Say, for example, f of z equal to z. If f of z equal to z, f of z half equal to half. It is not less than 1 by 4. It should be true for all functions. Similarly, mod f dash of 0 equal less than equal to half is also wrong. Okay. If I take f of z equal to z, f dash is 1. F dash of 0 is 1. Therefore, this is also wrong. So, only the second statement is right. The other three statements are wrong. Okay. Okay. The another question is, f is a d to d function. F of 0 is 0 and f of half is 0. F of 0 is 0, it is given. Okay. Therefore, I can use the lemma. Which of the following statements are correct? This is true that f dash of half less than equal to half 4 by 4. That you have to verify. What is given? F of half is 0 is given. I know alpha, I know beta, I know mu, substitute. If the inequality is satisfied, yes. If the inequality, that is a condition for the maximum value for f dash. If that is not satisfied, no. Here f of 0 is given. Therefore, mod f dash of 0 less than equal to 1 is right according to Scott's lemma. Okay. Here, if you verify the statement, if you verify the inequality, this inequality is satisfied. Therefore, yes, answer is yes, there is a function. Okay. Therefore, the mod f dash of, okay, one minute. This is true for every function. Every function it should be true because of this half is given. So this is also true, this is also true because both are true. This f of z is wrong. Note that what is f of half? F of half is 0. But it is given f of z equal to z. Z equal to half, what will happen? F of half is half but not 0. So fourth one is not true, whereas the first, second are true, and hence the third one is a combination of first and two is also true. Okay. Okay. Let f of z be analytic in the upper half plane. Suppose f of z is less than 1 for all z in the domain and f of I is 0. Find the largest possible value for this. We have used the sparse lemma to find that if f of alpha is known, beta is known, what is the maximum value for that? But here, what will happen? The image of some point is given. I want to find out the largest possible value for the some other point 2i. But the function is not a function defined on the unit circle. It is defined in the upper half plane. So I want to use a sparse lemma, means I have to do something. Okay. If there is a function, find one such one. Question is this. This is a net question, gate question. F of z is analytic in the upper half plane. Suppose the mod f of z less than equal to 1 for all z, and f of I is less equal to 0. What is that? What is given there? The image is in the unit circle, but the function is not defined on the unit circle. Function is defined in the upper half plane, but image goes to the unit circle. Somehow I want to convert this into circle. Okay. I consider this. What is the function? Function is given here. It is a function defined on the upper half plane. Function defined on the upper half plane to the unit circle. This I goes to 0. It is given. But I want to use sparse lemma. Therefore, I want to use a function from the unit circle to unit circle. So I want to get a unit circle to this one map. Combining this, I should get it. So here it is given that I goes to 0. Okay. I want to go to 0 goes to 0 means I want to map 0 to I, and then it goes to 0. Therefore, I want to get a map from this circle unit disk to the plane, upper half plane, which maps 0 to I. I consider map this. Phi of z equal to z minus I by I. Okay, that is a map reverse direction. That is a map reverse direction. When I equal to I here, when I equal to z equal to I, numerator is 0. Therefore, f of I is 0. Phi is a function from here to here. Phi inverse is this. When I, it is 0. Okay. What is phi of 2i? Phi of 2i is this. Note that how we consider this map. I want a map to map the upper half plane to the circle. I should go to 0. Note that I is a point. It maps to 0. Its conjugate, that is the symmetrical point is infinity. Therefore, symmetrical of I should go to infinity. What is the symmetrical of this I with respect to real? What is the boundary? What about the real axis? I is a point. Its image under the real one. It is z I bar. For z bar. For I bar is minus I. Okay. The minus I should map to infinity. That is why I put it. When I goes to 0, the minus I, when I goes to 0, the symmetrical point should map to symmetrical point. Therefore, its symmetrical point should be mapped to infinity. That is why we put it. When z is real, say for example 4. 4 minus I by 4 plus I, modulus value is same, equal to 1. Mod z minus I equal to mod z plus 1, and z is real. So this real line is mapped to the boundary of the circle. Therefore, this phi is a map which takes the upper half plane in the interior of this and the real line to the boundary of the circle. Therefore, this is a map from here to here. This is a bilinear transformation which is 1, 1 on 2. Therefore, I can find the reverse map. Reverse map maps 0 to I. So take the reverse map and follow by f. I get a composition map G equal to f circle this. This satisfied 0 goes to I goes to 0. This is a map from unit circle to unit circle, 0 map to 0. So I can use a sparse lemma. By sparse lemma, okay, this is sparse lemma. Mod f of, I have taken point as psi here and a point z there. Mod g of psi less than equal to psi for all. Okay. But in particular, I want the function value 2i. 2y is the image of what point? 2y is 1 by 3. If I substitute 1 by 3, is it equal to, if I substitute 1 by 3, if I substitute 2i, I get 1 by 3 here. 1 by I is mapped to 2i. When psi equal to 1 by 3, by this formula, mod phi of psi is less than equal to psi, mod g of 1 by 3 less than equal to 1 by 3. But what is mod g of 1 by 3? Mod g of 1 by 3 is 1 by 3 mapped to 2y mapped to this. So 1 by 3 goes to 2y and f of 2y. So this value is nothing but f of 2y. So mod f of 2y less than equal to 1 by 3. Okay. So if the inequality is true, so what is the maximum possible value? Maximum possible value is 1 by 3 only. So mod f of 2y is a maximum value is 1 by 3. If it is equal to 1 by 3, then the function is constant because it attains a maximum value here because the equation is there inside. Therefore, f of 1 by 3 equal to 1 by 3. So g of f psi equal to lambda psi, where lambda is 1, I get the value is this is the function. Once again, the original function is given from the upper half plane to unit circle. I know I is mapped to 0. I convert this, I get a map phi z minus I by z plus I, which maps the upper half plane to the interior, and go reverse map phi inverse. Composition map is just a composition map. The composition map is a unit circle to unit circle map and also takes 0 to 0. Hence, by Squarce lemma, I get the inequality. So maximum value for this is 1 by 3. So what is the previous question? Question is this is what is the question? What is the largest possible value for this? I have answered that the largest possible is 1 by 3. So f of 1, if find one such function, there is a question also there. Okay. Find one such function is also the question there. Therefore, that answer is also given equal to just the value. Okay. So we have answered that. (24, 25), and then I'll come to 26. Now consider this question. If the page order is different, therefore I have been saying these. Let f be an entire function. It's an entire function given. A is set of all points where the derivative of z f equal to 0 for some n, nth derivative. A is set of all z where at least one derivative vanishes at that point. Either f dash of z 0 or f square of z 0, f nth derivative is 0 or n plus 1th derivative is 0. At least one derivative is equal to 0 at that point. The set of all point where at least one of the derivative of f vanishes, at least for one n. Okay. Then what will happen? The question is, if A equal to entire plane, all z satisfy that. That means for any z, at least one derivative of f is 0. It is given. Can we conclude that f is a polynomial? Is f is a polynomial? A equal to c, can we say that f is a constant function? F is any function, any entire function. It's a constant function. It should reduce to constant function. If A is c here, instead of that, if A is uncountable, then f is a polynomial. If A is uncountable, then f is a constant. So there are 4 questions. First 2 questions, we have assumed that A equal to C. The second, third, and fourth, they are assumed uncountable. That's all. Okay. Now you can answer this. What about this A equal to C? For every point, f1 of z equal to 0. Assume that f is okay. Now, that A can be written as the set of all points where f dash is 0, union set of all points where f square is not equal to 0, union where the third derivative is equal to 0, union nth derivative is 0, I can write the union. So A can be written as a union of sets. Each set is n is fixed. First set f first derivative is 0, second set second derivative is 0, third set third derivative is 0, like that. So A is written as union of A1, union A2, union AN, dot dot dot, where n means the set of all z where nth derivative vanishes. So my C, we assume that A equal to C here, therefore A is written as countable union of A1, union A2, union etc. etc. But what is A equal to C is uncountable. We are simultaneously answering both questions. C is uncountable. But A is a union of countable union of open sets. Sets. So one of the set is uncountable. Either A1 is uncountable or A2 is uncountable or AN is uncountable, some set. Because if everything is countable, we know countable union of countable set is countable. But A union is uncountable given. But A is a countable union of sets here. Therefore, at least one set is uncountable. Say AN is uncountable. That means the set of all points where nth derivative is equal to 0 is uncountable. What can you say about the nth derivative? Nth derivative vanishes at countably many points. Can you conclude that that function is constant? If the function is a non-constant function, then zeros are isolated. Given a 0, I can find a neighborhood which contains, this is the only 0, it will not contain any other 0, isolated. So that can be only countable number of zeros for a non-constant entire function. Okay? If there are infinitely many zeros are allowed, but uncountable is not allowed. Okay? If there are uncountable number of zeros for a function, then function is a constant. What will happen? Since A equal to union of A1, U2, AN, at least one of them, say AN is uncountable. That means that nth derivative vanishes at countable number of points. Then that function should be a constant function. That which function? Fm is constant function. Fn is constant function. If you assume that n is fixed and is equal to 0 for uncountably many n, many z, then nth derivative of z vanishes at uncountable number of points. Therefore, nth derivative is a constant. Nth derivative is a constant means f is a polynomial of degree at most n. Nth derivative is constant means degree is at most n. So answer is, first answer is right. F is any polynomial. Okay, polynomial of degree less than equal to something n. But this is constant function is no, it is not suitable for constant function. Also okay, but for any such entire function, this is not common to all. We have used to argue this f is a polynomial by just using that c is uncountable. That's all. We have not used any other property other than uncountable. Therefore, the third one is same answer. Yes. Fourth one is wrong. First one is always true. Third one is always true. The second one need not be true for every such entire function. Fourth one is also not true for any such entire function. Okay. Right. Now another question. All these are net questions. Slightly, this slide may not be visible for you, only this slide, but I will read the question. Let f be an analytic function defined on the open disk U. Okay, it is defined on the open disk U. The function is constant if f of 1 by n equal to 0 for all n. N is a natural number, n equal to 1, 2, 3, etc. F of 1 by n is 0 for all n. F of z equal to 0 when mod z equal to half. F of 1 by n square equal to 0 when n greater equal to 1. F of z equal to 0 when z lies in the interval -1 to 1. What is the first question? First question, f half 0, f 1 by 3 0, f 1 by 4 0, f 1 by 5 0, etc. etc. Second one is when z is on the smaller circle with the radius half. This circle, smaller circle of the radius half, for all these points, the answer is 0. What about the third one? 1 by 4, 1 by 9, 1 by 16, 1 by 25. At all these places, answer is 0. The fourth one is when on the real axis, from -1 to 1, from this to this, when Z lies on the real axis in the unit disk, this answer is 0. Can you conclude that F is constant in each case? First case, what about the 1 by n, sequence 1 by n? Sequence 1 by n is half, 1 by 3, 1 by n tends to 0. The sequence has a limit point. Limit point is also in the same domain. Therefore, the function should be unique. But it already coincides with the 0 function. Therefore, it is a 0 function. It is constant. The function f is a 0 function, constant function. Second one, similarly here, I take this f is 0 on these points. I can take a sequence here. Okay, the sequence converges to -1, which is also domain. So the value tends to 0 everywhere. Therefore, the function is a constant function, 0 function. Similarly, for 1 by n square, because 1 by 4, 1 by 9, 1 by 16, 1 by 25 is a sequence converged to 0. 0 is also in the domain. Therefore, function is uniquely given by this value. Similarly, here, I take once again, on this, it is equal to 0. Already 1 by n, etc. 0 is given. 1 by half 0, 1 by 0. All these points are here. Therefore, that is also equal to 0. So, in all the cases, each one of the cases, f is a 0 function. Okay, this is a net question. Okay, simply you know that the uniqueness theorem, that's all. Uniqueness theorem for analytic function if the sequence converges. Next question, let U be a unit disk, let f of z equal to u plus b be an analytic function defined on U. F of z is given by a power series, a n z power n in the power series. Then f is a constant function if f bar is analytic. F of half is u of u. What is u? U is a real part. U of half is equal to u of z for all z in the unit. And a n equal to 0 for infinitely set. And for any closed curve, this equal to 0. Okay. Note that if f is analytic, f bar is not analytic, provided f is not constant. If f is analytic and also f bar is analytic, the function should be constant. Okay. And this is the maximum modulus theorem. The half is inside us. Inside that, the value attains the maximum value. Maximum value. U is a real part, not f. Real part is a harmonic function, real harmonic function. Real harmonic function also satisfies the maximum principle. So a function, real harmonic function cannot assume the maximum value in the interior, and provided it is not constant. Here it says that u of half is greater than equal to this, means it attains the maximum. Therefore, it is a constant, because harmonic function also satisfies the maximum principle. Real part of imaginary parts of analytic functions are harmonic functions, we know already. And this a n equal to 0. That need not be. Say for example, sin x, sin z. What is the expansion for sin z? Sin z minus z cube by factorial 3 minus is plus z power by factorial 5. There is no z square term, there is no z power 4 term, there is no z power 6 term. So a2 is 0, a4 0, a6 0, infinitely is 0. But it is not a constant function. Sin is not a constant function. Third one is not true. The fourth one is true. Use the property. Okay. Now, let f be c to c be an entire function. Can you conclude that f is a polynomial if for any a f of z is then a n equal to 0 for at least one n? Okay. And limit f of z equal to infinity. Limit z tends to n, f of z is less than equal to m for some m. Mod f of z less than equal to m into mod z power n. Already we had discussed. What is that? What is an? It is the entire function. Okay. An is nothing but if you write as a power series, an is f dash of fn of a by factorial n minus 1. If you know the Taylor's expansion, f of a plus f dash of a by factorial 1 into z minus a, f double dash of a by factorial 2 into z minus a whole square, etc., etc. So this an is nth derivative of f at a by factorial n. If an is 0 for at least one n means for each a, either f dash of a is 0 or f double dash of 0 or like that. So for every a, at least one of the derivative vanishes. Just now we have seen that if f dash vanishes at every point for some a, okay, if a equal to c, where a is the set of all points where some derivative vanishes. If some derivative vanishes at every point, then it should be a polynomial. Just we have concluded that the same repeated in a different language, that's all. Okay. So first one is a polynomial. So some nth derivative is a constant from zero function, therefore it is a polynomial. This means that infinity is a pole. Z equal to infinity means Z equal to infinity is a pole. Infinity is a pole if and only if the function is a polynomial. Otherwise, it is not. There is a theorem. We will do that theorem later on. If an entire function, infinity is a pole, the function should be a constant. Okay. Same thing. This means that f is bounded. Okay. That f is bounded. Note that the infinity is a pole, means the function is a polynomial. If f of z is such a domain, the function is bounded. It means that it's a bounded entire function. Bounded entire function is a constant function. Bounded entire function is a constant function. And the next one, the fourth one, is already we see that as a theorem, it is a polynomial of degree at most n. Degree at most n. Okay, that is also true. Okay, what is the value of the integration of this? Note that mod 1 minus z equal to 1. Therefore, this is a circle with the center 1. This is a circle with center 1, radius 1. What are the points? The function is not undertaken when the denominator is 0. When z square equal to 1, z equal to plus or minus I. Sorry, z equal to plus or minus 1. Z square equal to 1, z equal to plus or minus 1. Plus 1 is the center here, minus 1 is outside the center. Therefore, I can write this as e power z by z minus 1 into z plus 1. Okay. Z plus 1 I can take it. E power z by z plus 1 I can take it. Denominator is z minus 1. It is the formula f of z by z minus a. 1 by 2 pi I integration f of z by z minus a dz equal to f of a formula. In this case, f of 1. Okay. The 1 by 2 pi is not given. Therefore, this value is 2 pi I into f of 1. What is f? E power z by z plus 1. Substitute z equal to 1. Get the value. One of the answer is wrong. Right. Okay. The value is e plus 1 by e. You can get it. Okay. I have to go to 31. I have to go to 32. Okay. I'll come to this. It has to be an analytic function in the disk, open disk, delta. Some disk, the radius is not given, center is not given. Some disk is given. C is a circular disk inside there. C is a circle here. D is some disk. C is drawn as a circle with center within that, and radius is that. The entire portion is within delta. Such that f of z is not equal to 0 on C. On the circle, f of z is not equal to 0. On the circle, f of z is not equal to 0. Okay. The f of z may be 0 inside the circle. Where is this? Inside this, there may be 0. But on the boundary of C, there is no 0 for that. The number of zeros, n be the number of zeros f of z inside the circle. Then the n is given by the formula. This formula is already, you know, this is the argument principle. I'm just stating this only, but I'm not going to use it now. 1 by 2 pi I integration over C f dash of z by f of z d is equal to n, where n is in this. So this C is here. What about the image of C? Image of C is some curve. As you move from this point on the circle C, I move from here along the circle, so some curve coming back to the original position, but it will not pass through 0. It has makeup. So it makes how many rounds? As this moves like this here, this makes how many rounds around the 0? If there are 4 rounds, means there are 4 zeros inside this. But if this makes only 1 round here. This here, I make 1 complete round, one around 0. Okay? So in this case, answer is 1. Suppose the curve is like this, as you see, as z moves on this, the image f of z moves on this, like this, like this, like this, makes 7 rounds. Then there are 7 zeros inside this. So theorem says that the function f maps C onto a closed circle. Then the number of zeros n is nothing but the winding number of 0 with respect to the gamma. That means how many rounds it makes. If it makes 4 rounds, positive means answer is 4. Okay, it makes only like that. This theorem I'm not going to use it, but this is good. Okay, 32. Okay. Okay. Another theorem is there. I have not included in this. That is called open mapping theorem. Open mapping theorem says that a non-constant analytic function takes open set to open set. Image of every open set is open. If f is a function analytic defined on a domain D, and if A is any open set in the domain D, f of A is also open. It takes open set to open set. That theorem is called open mapping theorem. For that only I need the previous one. To prove that only we assume that open mapping theorem. We are not going to prove it now. I'm not going to prove the argument principle theorem and also open mapping theorem. But open mapping theorem is more important. F is analytic means it takes open set to open set. That's all. Open mapping theorem. Okay. I consider that. Now coming to this. The maximum principle of analytic function can be deduced from the open mapping theorem. Okay. We know what is open mapping. It takes open set to open set. That's all. Simply assume that. Let f of z be a non-constant analytic function in a region. Region is connected open set. Z0 is an interior point. Then there is another point Z1 in the domain, such that mod f of z0 is strictly less than mod f of z1. Mod f of z0 is not maximum. There is something one which at times is more value than this. If f of z0 not equal to 0, then this value is not minimum. If mod f of z0 is not maximum, If f of z0 is 0, it is only minimum value. If f of z0 not equal to 0, then mod f of z0 is not a minimum value. So there is another point z2 such that mod f of z2 is less than. So if maximum principle says that f of z0, mod f of z0 is not maximum. If f of z0 not equal to 0, it is not minimum. Okay, we can prove it. Very simple proof here. We can give that f of z be a non-constant analytic function defined on the domain. This is the domain here. Okay, this is open set. Therefore, image is open set. This is the image of f of omega. F of omega is here. Can you able to see that f of omega? It is an open set. Okay, z0 is a point. Its image is f of z0. Is w0 is an interior point. Note that this set is open because omega is open, its image is open. Since omega naught is there, it is an interior point. Therefore, I can find a small circle disk with center omega naught, which lies entirely within the open set. Note that it is an interior point. Therefore, I can find an interior neighborhood, open ball around center omega naught, which lies here. Now, omega naught is this point. Now, join 0 to omega naught. It is 0 to center of that circle. Now, slightly extend this length of the line segment. Please simply extend further. Take some point on W1 on that. Okay, so 0 modulus omega naught is this length. Modulus W0 is this length, bigger than that, because I have taken such that. But W1 is also here. That means it is in the image. Therefore, it is an image of some point. Therefore, there is a point Z1 whose image equal to W1. Once again, Z0 is a given point. Its image is omega naught. Omega is open set. By open mapping theorem, its image is open set. So omega naught is a point in the open set. Therefore, I can draw a small circular disk with the center omega naught lying within this. Join 0 with that. Slightly extend. Fix a point there. This point is in the image set. Therefore, it is image of some point. What about mod of omega 1? Mod W1 equal to this length. Okay. Mod W1 is this length. Mod omega naught is this length. So mod f of z0 is less than, strictly less than mod f of z1. So I am able to get it. Okay. Suppose omega naught not equal to 0. If omega naught equal to 0 means I can take a small circle, any point will satisfy this. So if omega naught not equal to 0, take a point here. First, I line segment extended. I take W1 to show that the value is not maximum. To show that the value is not minimum, I take another point within the circle, but less than this, below this. I take a point. This W2 is a image point. W2 lies in the image. W2 lies in the image. Therefore, it is image of some Z2. What about the mod Z2? Mod f of Z2 is this length, strictly less than mod omega naught. So I get it. So I get a simple proof for the maximum modulus theorem and minimum theorem using the open mapping theorem. That is why I have omitted the proof there. Now as the open mapping theorem, I get this. Okay. F be a non-constant analytic function in the unit's disk such that f of 0 is 0. Okay. Non-constant is given. Unit disk is also given. The function unit disk 1 such that f of 0 is 0. The function is not given as a function from the unit disk to unit disk. It is given, defined on the unit disk. That's all. Okay. The f of 0 is 1. Then it is necessary that for every such function, is it possible, is it true? There are infinitely many points you said in the disk with the same value. Note that f of 0 is 1. Okay. So mod f of 0 is 1. Can you find many other points like this, infinitely many points such that mod f of z equal to 1? Can you conclude by this that f is a bounded function? Can you conclude from this that there were the first one is infinitely many? No. For every such f, there are only finitely many. There is another alternative. First alternative gives there are always necessary that always there are infinitely many points. The other alternative is always there are only finite number of points. Okay. And the fourth alternative is a rational function. There is a net question. Note that f of 0 is 1. It is a non-constant analytic function defined on the unit disk. The range may be anything. F of 0 is 1. Is it compulsory to show that it has infinitely many points with the mod f of z equal to 1? F is bounded. There are only finite number, a rational number. This is a very good question. I will answer this question now. Okay. First, what is a simple first f is function f is bounded? It is wrong. It need not be true because it is necessary here. It is not necessary for every such function. There are some functions which is bounded. There are some functions which are not bounded. Okay. First, I will prove that. Take the function f of z equal to 1 by z. 1 by 1 minus z. Note that z equal to 1 is a pole. When we put z equal to 1, denominator 0, therefore infinity, therefore z equal to 1 is a pole. So whenever from this circle, if I approach 1, the value approaches to infinity. Therefore function is not bounded. Mod f of z. Take, no, it is not necessary to take 1. Take any point a on the boundary. Consider the point 1 by z. Z equal to a 1. This z tends to a, f of z equal to infinity. Therefore function is not bounded. So such a function need not be bounded always. The last choice is the function is a rational function. Is it a rational function? The function f need not be rational function. For example, f of z equal to e power z. What are the conditions given there? What are the conditions given there? The function is a non-constant function. F of 0 is 1. That's all. The function is f of z equal to e power z is a non-constant function. F of 0 is e power 0 is 1. But it is not rational function. The expansion is 1 plus z by factorial 1, z square by factorial 2, go on. It is not a polynomial by polynomial. It's not a rational function. So second choice is wrong. Fourth choice is also wrong. So only thing is I have to prove the first choice or third choice. Okay. I'll try to prove this. Somewhere in the domain, so I need not take unit circles. It is general. Generally, we can answer the first question like this. In some domain, df is analytic function. Z0 is a point here. Z0 is a point here. I know the image. I know the image W0. W0 is image of this. Note that D is open set. Therefore, its image f of D is also open set. And W0, the image of point is here. It is an interior point. Therefore, I can draw a circular disk within this open set. I can find a smaller circular disk with center omega naught such that the entire thing lies in the open set f of D. I can draw this. Okay. Now, what is the question? Can we find infinitely many points such that mod f of z naught equal to mod omega naught? Mod omega naught is known. If mod f of z equal to mod omega naught means f of z should lie on a circle with the center 0 and radius mod omega naught. This is 0 here, W0 here. I now take the mod omega naught as a radius. As radius take it drop. The question is, can you find lot of points on this domain, on the circle, which also lies this? Now see the picture. The circle with radius omega naught passes through omega naught. Omega naught is the open set and a circular disk. Therefore, this circle, consider the circular disk. The circle passes through the center of the circular disk. Therefore, if it travel along the circle on this, somewhere it should enter the disk and passes through the center and then I had to leave it. So this portion of the circular arc, the circle intersection with the disk is this arc. For every point is a point in f of d. So every point is a image of some point. So this is the image of z0, this is an image of some other point, this is image of some other point. So each point is an image of something else. How many points are there? If what about image of w? Image of w is some z. But z is not equal to z0 because z0 image is w0. Z image is w, which is not equal to w0 here. So for different points here, I get different values here, images. So for every point on the arc, I get a point here whose image is this. This arc is uncountable set. Therefore, I can find uncountable number of z here whose image lie on this. Therefore, there are infinity, not only infinitely many, uncountably many points z satisfying this property. So if the map omega is analytic domain, z0 is then f of z0 is not zero. Not zero is more important. If it is zero, the circular bit modulus is more than that, not zero. Okay. Then there are infinitely many points z in D such that mod f of z. This is so what will happen? What we have proved. First one, there are infinitely many points z in the disk of such that this is true. For all f, not only single f, for every f satisfying the property f of 0 is 1. I have proved generally instead of assuming I knew the f of 0. Therefore, the third one is wrong. Okay. Third one is wrong. Next question. I have done it 39. Okay. F C to C, sorry. Be a non-constant analytic function. It is a constant, not constant analytic function. Which of the following is or false? The function f is unbounded. Note that it is non-constant analytic function defined on C. That means it is an entire function, non-constant entire function. The function is unbounded. F sends open set to open set. There exists an open set correct domain in which f never vanishes, attains its minimum at some point. The image of f is dense in C. Okay. So what is given? F is a non-constant entire function. This is Liouville's theorem. Every non-constant function is unbounded. Bounded entire function is constant. That is a theorem. Therefore, it is non-constant. It is unbounded. So first one is that. The second one, f sends open sets to open sets. It is an entire function, non-constant. Therefore, it takes by open mapping theorem. Image of open set is open set. So it takes open sets. It takes open set to open sets is given. Therefore, this is also true. And what about the last one? Image of f is dense. Note that f is a non-constant entire function. Non-constant entire function by Picard's theorem. Image is entire complex plane or complex plane minus 1 point. It can omit at most 1 point. Okay. So image f of z image is entire C or C minus a single point. In both cases, it is dense. So fourth one is also true. Okay. Third one, there exists an open neighborhood. Yes. Within the open neighborhood, restricted to the open neighborhood, consider the f within the neighborhood. This is not 0, but attains a minimum. The maximum minimum theorem we have found out. If f of 0 is 0, sorry, f of z is not equal to 0, then mod f of z is not minimum value. So it is never 0 means f of z, mod f of z is not the minimum value. So it will not attain the minimum value anywhere. So the question is, what is the question? Third question. There exists open set where nowhere 0, but it attains a minimum. Is a wrong answer. Maximum. These are the statement of the theorem. This is Rayaueri's theorem. This is open mapping theorem. This is the maximum modulus the minimum theorem. This is a little Picard theorem. Just they have worded the 4 different theorems as a single question. Entire function, unconstant type function is not bounded. It sends open set to open set. If it is not 0, it will not attain the minimum value. It is dense there. Okay. Okay. Huh? Water கொஞ்சம் வெந்நீர் இருந்தா கொடு கொஞ்சமா. Okay. Come to the next question. Phi is a map from C to C, but not C. At the point 1 is not defined. At the point 1 is not. At the point 1 is not defined. Except 1, the function is defined by this. Phi of z is 1 plus z by 1 minus z. Don't that this anti-function. Except where the denominator equal to 0. Denominator equal to 0, z equal to 1. Z equal to 1 is a pole. That is why they have omitted 1. So they have omitted 1. This function is analytic everywhere except 1. That point is omitted. Therefore, this function is analytic function from here to C. Which of the following is true? Okay. The image of the unit circle is contained in the image of this circle. Okay. Note that if Z is real, what will happen? Okay, let us consider this. Note that this is a binary transformation. 1 plus Z by 1 minus Z. When Z is real, is 1 plus A by 1 minus A. Okay. What is given here? Mod Z doesn't. What about the circle? There's a circle. This takes when Z equal to 0, what will happen? Z equal to 0 value is 1. Z equal to half, what will happen? Minus half, what will happen? Z equal to minus half, what will happen? Z equal to minus half means 1 minus half is half. 1 minus half minus half 3 by 2 is 1. Okay. Z equal to half. This is 3 by 2. This is half. The answer is 3. Phi of 3 is just. Phi of half is 3. When half satisfies this property, but the image is 3 is not within this. This is not true. Because this takes the circle into the imaginary axis. This is a binary transformation. It maps the circle. Which circle? Unit circle into the imaginary axis. Therefore, interior of this should be the imaginary axis divide the plane into 2 parts. One side of part where imaginary part is real part is positive. Other side is imaginary real part is negative. Therefore, this interior of the circle is mapped in the half plane. Half plane cannot be contained in a circle. Therefore, first one is wrong. If you want, you can take Z equal to half. Value is that. Real Z less than 0 is this. Once again, I have taken that Z equal to half, minus half. Z equal to minus half. Real part is negative. But what about the imaginary part? This is made. This is this question is F. This is F of Z. I have write F of Z. F of Z less than C real part. F of Z is half. The same thing twisted. This phi is onto. Is take every value here. This is this value will not take when he said can this be equal to 1? Okay. Can 1 plus Z equal to 1 minus Z equal to 1? Note that this 1 is mapped when Z equal to 1, the value is 0, infinity. The denominator is 0, therefore infinity value. Therefore, infinity is mapped to 1. Okay. What about infinity value? When Z equal to infinity, what will happen? When Z equal to infinity, what is that is find the limit? Z tends to infinity. That is equal to the coefficient by this coefficient is minus 1. Minus 1 is not a value of this. Can it be equal to minus 1? 1 plus equal to 1 minus of 1 minus z. That means 1 plus z equal to minus 1 plus z. 1 equal to minus 1 is wrong. Therefore, there is no point here such that value is minus 1. Okay? Because at minus 1, the value goes to infinity. Therefore, the value is not 1 there. So, the phi is not onto. What about the image? Phi of this. Okay. Which point is omitted? Infinity is, this has everything except infinity and 1. At infinity, what will happen? At infinity, value is minus 1. So that is omitted here. At 1, it is infinity, that is also omitted here. Therefore, this answer is right, correct. Equal to is correct. The fourth one is correct in this sense, in this way. Okay. Now consider the function f of z equal to e power z. Which of the following statement is false? Note that the question is which is false. F mod z less than 1 is not an open set. Mod z less than equal to 1 is not an open set. Mod z equal to 1 is a closed set. The image of the outer side is an unbounded open set. Okay. These are the questions which are wrong. Mod z less than 1 is a unit disk, open unit disk. F is an analytic function. It takes open set to open set. Therefore, image of this should be an open set. But what is given? F of z is not an open set. Therefore, this is a wrong answer. False. The result is false. Therefore, I have to make a tick. This answer is correct. Because the answer is false question. Which is false? This statement is a false statement. Therefore, 1. But this is mod is less than equal to 1 is a closed set, compact set. Mod is less than 1 is compact. Image of a continuous image of a compact set is compact. So image of this is a compact set. Compact set is always closed, but it is given as a not open set. Not open set is okay because C is closed set is not open in C. So image of the compact set is not open. It's correct statement, but it is not. You should not make correct. It is a correct statement, but it is not a false statement. And z equal to 1. Once again, it's a compact set. Image is a closed set. It's a correct answer, correct one. Therefore, it's not a false statement. And mod is less than 1, greater than 1, is unbounded set. This e power z. There, say for example, mod is greater than 1. Take 2, e square. Take 4, e power 4. Take 6, e power 7. 100, e power 100. It goes to infinity. So image of the outer of the unit circle, exterior of the unit circle is unbounded set because e square, e power 4, e power 6 is increasing. E power n increases to infinity as n tends to infinity. Therefore, it is unbounded. This is also a correct statement. It is not false statement. So this is correct statement, correct statement, correct statement. This is only the false statement. You are asked to pick out the false statement. So your answer is the first statement is the false statement. Okay? 45 to முடிச்சிருப்பேன். Let P of Z and Q of Z be non-zero polynomial. Then P of Z, Q of Z bar is analytic if and only if. This is also net state question. But the key given by net examination is the wrong answer. The correct answer I will say it now. That P of Z and Q of Z be non-zero polynomial. Okay. Then P of Z, Q of Z bar is analytic if and only if. P of Z is analytic. P of Z is constant. P of Z, Q of Z is a constant. Q of Z is a constant. P of Z bar, Q of Z bar is a constant. Note that if Q of Z is constant, Q of Z bar is also constant. P of Z is a polynomial. Okay. So P of Z is a polynomial analytic function. Where is it? P of Z is an analytic function. P of Z, Q of Z bar is a constant. Q is constant means Q of Z is constant. Constant into analytic function is a analytic function. Therefore, it is right. If Q of Z is constant, okay. If this is analytic, divide by P of Z. If this is analytic P of Z, any 0 of P of Z will cancel with the P of 0 of this. That is the entire function now. P of Z and the Q of Z by P of Z. P of Z may have zeros. There may be a point where which cannot be defined, but those point brackets can be cancelled with this. Therefore, remaining is Q of Z bar. That is analytic. But Q of Z also analytic. Q of Z bar is analytic, means Q of Z is constant. Yes. This is if and only if C is the correct one. Note that. If Q of Z is constant, this is constant, therefore analytic. If this is analytic, consider the P of Z, Q of Z by P of Z. It is defined everywhere except where denominator not 0. But at denominator 0, that denominator 0 cancel with this 0. Therefore, those points are regular points. Therefore, this function is P of Z, Q of Z by P of Z is an entire function. That P of Z has cancelled, Q of Z bar is an entire function, analytic function. But Q of Z analytic and Q of Z is analytic means Q is a constant. That's if and only if this. P of Z not constant is not true. You say 4. Then Q of Z bar is analytic. Q of Z is also analytic. Then Q is a constant. Therefore, this is not a correct answer. This is also not a correct answer. This is also not a correct answer. Note that this is nothing but conjugate of that. This is analytic. Conjugate of that is analytic. It is not constant. Okay. So the only correct answer is C. Okay. Whereas in some books, they are given as this as wrong key. This is the correct answer is Q of Z is constant if and only if this is analytic, when P and Q Z are non-zero polynomials. Okay. 42. This is another good example. Let B be an open set of C and this is a boundary. Okay. B is an open subset of C and boundary of that is denoted by this. Which of the following statements are correct? For every entire function, the boundary of the image is subset of the image of the boundary. Okay. Boundary of the image is less than equal to image of the boundary where B is an open set. Second question, same question, but restricted to bounded open set. Restricted to bounded open set. Third question, he says that equal to. Fourth question, I can find one unbounded not satisfying this property. Okay. So first question is there is no restriction on the open set. Open set may be bounded or this second one bounded. First one may be bounded or may be unbounded. Is it true for such a B? Image boundary of the image is subset of the image of the boundary. Okay. Now I will give the answer for this. This is a very good question. Now consider the first one. What is the first one? I want to show that this is wrong. This wrong means I can find a suitable function and suitable open set such that this condition is not satisfied. Okay. For that, I consider this. I consider the function f of z equal to e power z. I consider that the left hand side of the imaginary axis, that is where the real part is negative, where the real part is negative. My open set is where z real part is negative. My function is e power z. E power z takes the entire line imaginary axis to the circle. E power I theta, I pi varies over this. Image of this imaginary axis is this. For one, e power 1 is outside. For this, inside this. So e power z takes this imaginary axis to the circle, this part to the interior of the circle, and this part to the exterior of the circle. So this is, I take this as an open set. What about the image? Image is in the interior. Note that e power z will not take 0. Nowhere e power z is 0. So 0 is not in the image. The boundary is also not in the image. For this, boundary is on this. So what about the image? Image is, what about the image? Image is, image is this is 0 less than mod omega less than 1. The image of B is the annulus portion 0 less than mod omega less than 1. What about the boundary of this? Boundary of this is this imaginary axis. What about the image of the boundary? Image of the boundary is this circle. But what about the boundary of this region? Boundary of the region is this point is also included. This is also not in the region. Therefore, that is also boundary point. So boundary point of that is 0 included the upper circle. So boundary of this is this, image is this. Therefore, this has one more. Okay, this has one more. 0 is there, it is not included that. This has 0 union this, whereas this is this only, 0 is that. Therefore, this is not correct. Note that I have also given an example, a function with unbounded, not like that. Okay, so this is also answer for the fourth question. It's also answer for the fourth question. There exists an unbounded open set such that this is not such that is also there. So I want to answer the second and the third. Second one is every entire function, any bounded set. So open set is bounded here. The previously I had taken the open set unbounded. What will happen if it is bounded? Okay. The statement B is correct. If B is bounded open set, what about the closure? B union sigma B. B is bounded, boundary also, it is bounded closure, therefore it's a compact set. So F is analytic, it's a continuous function. Image of a compact set is compact, therefore F of this also compact set. Note that B is subset of this. Therefore, image of subset is subset of this. But what about this? F of B is contained this. This is a closed set. Therefore, closure of this is contained with this. This is the closed set. This is F of B. Therefore, its closure, F of B bar is contained this. F of B bar is the F of B union boundary. F of B union boundary is contained this. This is F of B union boundary. Note that B is an open set. B is an open set means B and sigma B intersection is empty. Okay. F of B is also open. Therefore, open set with its boundary is also empty. Open set will not have boundary, will not contain the boundary points. Open set, there is a boundary set there, but open set will not contain the boundary point. This intersection is empty. Note that if this is a point, okay, that will be only here because this set has intersection with this is empty. Therefore, this set is contained only this. So sigma p. So if it is bounded, F of B is open and B union sigma B is a compact set. F of this is a compact set. B is a subset of this. Therefore, F of B is a subset of this. This is a closed set. Therefore, closure is the smallest closed set containing this. Since this and this has no common point, this is entirely contained within the last one. So the second one is correct. Okay. I want to give the fourth one. What is the fourth? What is another one? Another one. Okay. Okay. For the entire function, F of B could be if B is bounded. Okay, it's subset only given. I have to show that equal to. Is it possible to give the equal to? It is true for necessary. It is not true. Consider this function, this set. Consider this set. What is the set? Minus 2 pi to 2 pi. This is minus 1 to 1. Go up to 4 pi I. Below minus 2 pi I. Up to this part is open set. It is a bounded open set. My function is e power z. What about boundary of this? Boundary of this is this and this and this and this and this. Okay. Image of B. Image of B is this. Image of B is when z equal to 1, e power 1, 1 by e. Entire circle, this is mapped in the circle, 1 by e. This is mapped to 1 minus 1 by e. Okay. So this is mapped to, this is the boundary circle is e power 1. This is 1 by e. Small circle is there. This boundary is 1 by e. This circle is this. So the image is in between the two circles with center 0. With the smaller circle radius is 1 by e. Bigger circle radius is e, because e power 1 is e power minus 1 is minus 1 by e. Okay. And what about the image of this? Image of this inside this. What about the boundary of this? Boundary of this is the circle plus this circle. Boundary of this is circle plus the circle. Okay. But what about the boundary here? Boundary here, etc. What about the image of this boundary? Image of the boundary. These points are in the imaginary axis. Map is e power z. E power z maps the imaginary axis in the unit circle. So image of this line is a unit circle. Unit circle lies completely within the disk, within this portion. It is interior portion. It is not the boundary of this. Okay. So this image of this boundary is an interior here. It is not on the boundary. Okay. So this is an example to show that the image of the interior need not be equal to this. Why we got it? Image of this, note that, take one point here, say I, minus I. The corresponding point is plus I. Okay, what about the image of that? So the image of that is inside this. So if this point is interior point, if this is interior point, that image is also interior point, therefore I can draw. But image, this point and this point will have the same point image. Okay. Therefore, if the function is not 1, 1, if a boundary point and the interior point take a value, same value, then this is not equal. Okay, this shows that. And finally, I have given already the example this. So this is the answer for the fourth one. With these things, I think it is better to stop at this stage. We have started with Maxim-Morris theorem and Scott's lemma, various versions of Scott's lemma, and the problems asked in the next question we have answered, and open mapping theorem, problems under open mapping theorem, and other things. I think with these things, I thank the organizer for giving me a chance to use this. Thank you once again. Can you hear me?
Yes, sir.
Okay.
Thank you, sir.
Thank you. Hello?
Sir?
Hello?
Yes,
can
sir.
you hear me?
Yes,
Okay.
sir. Yes, sir. Yes, sir. Thank you, sir.
Okay.
I thank our most distinguished resource person.
Hello? I'm not able to see your...
Now visible, sir.
Okay, I'm not able to see. Okay.
Thank you, sir. I thank our most distinguished resource person, Dr. N. Sridharan, retired professor and head, Department of Mathematics, Arugappa University, Karaikudi. Thank you, sir, for spending your valuable time in sharing your knowledge in view of motivating and encouraging students, research scholars, and teachers. Thank you, sir.
Thank you. Thank you very much. Thank you.
I'm very proud to inform about our upcoming programs. National level webinar titled Uniform Convergence, presented by Dr. P.S. Srinivasan, Assistant Professor, Department of Mathematics, Bharathasan University, which will be held on 28th November at 10:30 a.m. Our next program, C4, Chase, Crack, Conquer, CSIR Net. This is a free online coaching for CSIR Net aspirants. Classes will be on every Saturday 6 p.m. to 8 p.m. and every Sundays 11 a.m. to 1 p.m. Our 12th C4 session will be held on 28th November 2020 at 6 p.m. Thank you.